A two-shaft gas turbine draws in fresh air and compresses it to a higher pressure by means of an axial flow compressor. The compressed air is mixed with fuel in the combustion chamber and burned, increasing the energy level. The resulting hot gas is then expanded through the high-pressure turbine, where some of the gas energy is converted into mechanical energy that drives the compressor. The hot gas is further expanded through the low-pressure turbine that drives the load equipment. Finally, the combustion gases, now at a low pressure and temperature, are discharged into the atmosphere. To better understand the simple gas turbine cycle, it will help to first review the principles of a four-cycle reciprocating engine. In the four-cycle engine, production of power is intermittent. This happens because loss of combustion reaction pressure occurs due to the pressure drop involved in the exhaust stroke. During the air intake stroke, negative pressure is created in the cylinder. This causes atmospheric air to enter the cylinder. During the compression stroke, the air is compressed and the pressure begins to increase. At the top of the compression stroke, the pressure is high and the air temperature is increased due to compression. Fuel is injected and the fuel-air mixture is ignited. The combustion reaction produces extremely high pressure in the cylinder, creating the expansion or power stroke. During the exhaust stroke, the pressure is decreasing but is still higher than ambient pressure. The combination of high pressure and the motion of the piston forces the combustion gases out of the cylinder. In the simple gas turbine cycle, combustion and exhaust occur at constant pressure, and compression and expansion occur continuously rather than intermittently as in a four-cycle engine. This means that pressures remain constant in each section of the gas turbine: the compressor, the combustor, and the turbine. At point 1 in this diagram of the simple gas turbine cycle, air enters the compressor and is compressed to a higher pressure. The high-pressure compressor discharge air at point 2 is mixed with fuel in the combustor. The combustion gases at point 3 enter the turbine, where they expand and cool, performing work on the rotating turbine shaft. The combustion gases are then expanded to atmospheric pressure and exhausted to the atmosphere at point 4. Therefore, the major difference between a four-cycle engine and the simple gas turbine cycle is that the gas turbine produces continuous power, while the power from a four-cycle engine is intermittent. This means that power is available continuously throughout the operation of a gas turbine, but in a reciprocating engine, power is available only on the expansion stroke. The conversion of work in either turbine actually takes place in two steps. In the nozzle section, the hot gases are expanded and a portion of the thermal energy is converted into kinetic energy. In the subsequent bucket section, a portion of the kinetic energy is transferred to the rotating buckets and converted to work. To see an animation of the airflow through a two-shaft gas turbine, click on the Show Me button. Otherwise, click on Previous menu. The variable area nozzles divide the available energy between the high-pressure and low-pressure turbines. Opening the variable area nozzle decreases the back pressure on the high-pressure turbine. The pressure drop across the high-pressure turbine increases, causing the high-pressure turbine to generate greater speed and power. The main components of the combustion chamber are the fuel nozzle, cover, self-retracting spark plug or igniter, cap and liner assembly, and outer casing. The compressor discharge air has four basic functions. It is used as combustion air, primary air, to achieve the proper fuel-air ratio. It is used as secondary air to cool and stabilize the flame. It is used as cooling air to provide a continuous cooling film along the external and internal surfaces of the liner. And it is used as dilution air downstream of the primary combustion area to reduce the gas temperature and preserve the life of the hot gas path components. The combustion process works like this. Compressor discharge air flows through the annulus between the outer casing and the liner and enters the liner cap. Fuel is injected into the liner cap and mixes with the compressor discharge air. The fuel-air mixture is ignited by the spark plug. The hot and rapidly expanding combustion gases then flow to the first stage nozzles in the high-pressure turbine section. Once ignited, the combustion process is self-sustaining as long as fuel and air are available. The gas turbine is an ambient air-breathing machine. Therefore, its performance will be changed by anything affecting the mass flow of the inlet air to the compressor, such as changes in temperature, barometric pressure, and humidity. The temperature of the air entering the compressor inlet affects output, heat rate, and airflow. These effects are illustrated in this graph. In this graph, you can see how a compressor inlet temperature of 20 degrees Fahrenheit affects heat rate, airflow, and output. Click on the other compressor inlet temperatures to see how they affect the performance factors. Click on Previous Menu when you have finished. This graph shows the effects of altitude and barometric pressure on gas turbine performance. A decrease in air density reduces mass flow and output proportionally. Heat rate is not affected. For example, a unit installed at an altitude of 3,000 feet would require an atmospheric pressure correction of approximately 13.2. The correction factor for the output and fuel consumption would be approximately 0.91. If a gas turbine with a nameplate rating of 100 megawatts is installed at this altitude, the expected output would be 100 times 0.91, equaling 91 megawatts. Prior to assembling the high-pressure rotor, the compressor and turbine wheels are spin tested. Then the compressor blades are slid into slots in each compressor wheel. The blades are staked to maintain their positions in the wheel. Once assembled, each compressor wheel is placed on a rotating table and a belt sander sands the blade tips down to the proper dimensions as called for by specification. Locking blocks are inserted in the tie bolt cavities in the forward stub shaft. Tie bolts are screwed into the locking blocks. The forward stub shaft is then placed in the stacking pit with the tie bolts in the vertical position. The first compressor wheel is slid over the tie bolts. Then a wheel spacer and the next compressor wheel are slid into place. This is repeated until a total of 6 compressor wheels and 5 spacers are assembled. Once the last wheel is stacked, the aft stub shaft is slid over the tie bolts and the bolts are tightened. Plugs are inserted in the tie rod slots to prevent particles from entering the slots during turbine operation. The high-pressure rotor is then placed into the horizontal position on V-blocks. The first stage compressor blades are inserted into radial slots in the forward stub shaft and staked in position. Compressor blades for stages 8, 9, 10, and 11 are inserted into radial slots in the aft stub shaft and locked in place. The journals and sealing lands on the compressor rotor are finish machined and inspected according to specifications indicated on the assembly drawings. Prior to assembling the turbine wheels, both wheels are preheated. Tie bolts are screwed into the aft stub shaft, and the hot first stage turbine wheel, cold wheel spacer, and hot second stage turbine wheel are assembled. A locking ring is attached and the tie bolts are secured. Subsequent cooling of the turbine wheels reduces the clearances between the aft flange of the compressor rotor and the first stage turbine wheel and between the turbine wheels and spacer. The buckets are now assembled in the dovetail slots of each high-pressure turbine wheel. After the buckets are installed, locking plates are inserted between each pair of buckets and the wheel rim to tighten the dovetail fits. Each locking plate has a tab that must be bent and broken off using sufficient axial force to ensure that the locking plate makes full contact with the buckets. Once the high-pressure rotor is completely assembled, it is slow-speed balanced. Balance weights are inserted and staked in place to make sure vibration levels meet design standards. Wire the turbine wheels preheated before they are assembled to the rotor flange. Click on your choice, then click on Enter. That is incorrect. Please try again. Good. You are correct.